Hello everyone, I'm Professor Shijing Sun from University of Washington. Today I'm very excited to start a new lecture series on the application of machine learning. In particularly, we're going to discuss closed-loop optimization. So over the next 4 sessions, we're going to discuss what is open versus closed-loop frameworks, how to build a surrogate model, how to select the next experiment, and also we're going to go through a few Bayesian optimization examples in real-life engineering practices. Especially, you will find out there's an underlying theme across all 4 topics that we're going to discuss, that is data-efficient machine learning. So for today, we're going to focus on open versus closed-loop frameworks. We're going to discuss what is a closed-loop framework, why do we want to build one, and also how does Bayesian optimization help us here? Let's dive in. So optimization lies at the core of the engineering practice in our day-to-day life. From the early research of new materials discovery, to process optimizations, to the deployment of new technologies, such in this case the solar panels, there are a lot of experiments engineers conduct through all these periods, trying to find the optimal solutions that made into the final product. So the optimum solutions we are looking for example, maybe we are trying to fabricate a thin film semiconductors. We are interested in finding within the different temperature range, different learning time period, different addition of the additives. What are the conditions that it would yield the most desirable property of interest? For example, it could be the no defect thin films we are interested in, it could be the toughness of the materials we are making, and so on and so on. But there are 2 questions here. The first, when we have a vast parameter space, when we are trying to optimize, how do we find the maximum or the minimum property of interest within this large space? And second question, we have limited time and resources. How do we find our desired property within this parameter space quickly and ideally with the least number of trial and errors? So traditionally, we will conduct our research using an open loop framework. So that includes a linear workflow. We make some samples, we go to measure its properties, and from there, we generate knowledge base, and then we can make some predictions about the conditions we haven't tried before. For example, say we are interested in tuning the temperature processing windows to make our thin film semiconductors. So you may see as a function of temperature, let's say in Celsius, we are interested in figuring out between 100 Celsius degree to 500 Celsius degree, what would be the optimal temperature window for us to achieve the desired property of interest. So we'll make some samples, and we'll start to take some measurement. And from there, we started to draw some conclusions, saying maybe this is the trend of how the property changes a function of time. And we say, well, if we want to maximize this property of interest, these are some of the temperature candidates we can try out. So this exemplifies an open loop framework, a linear workflow for optimization. At this point, if we want to further optimize our process, we will take what we learned from the first experiment and start a next set of the experiment and further build our parameter space and try to optimize our process from there. So what does it mean by having a closed loop framework instead? So here we're thinking instead of having us, humans, taking what we learned from the previous experiment and then start to design the next experiment, we automate this process by having the decision making directly feedback to the next round experiment. In particularly, in this course, we're interested in data-driven closed-loop optimization In other words, we have a machine learning model trying to help us decide what would be the next set of experiments to run in order to accelerate the process for us to achieve our optimal conditions of interest. So out of the many closed-loop optimization strategies, Bayesian optimization is definitely among the most popular and widely used framework. In a Bayesian optimization framework, we follow a cycle like the ones shown on this slide. We will make some samples, conduct experiment to measure their properties. So that gives us the input and then the output. And using this data, we build a surrogate model with a representation of the true function that describes the input and output relationships. And from there, we started to use another term called acquisition function, which is a rule to help us rank the potential experiments and decide on the experiment we should conduct next. From there, we bring the decision back to the conditions we want to try and start the next round of experiment. So if we quantify what are some of the steps we can go through if we want to conduct a Bayesian optimization, we often will start with a problem formulation. That is where we define what is the objective function of our optimization task. What are some of the search space we are interested in? And what are the input parameters and the feedback, which is the output we are interested in measure. From there, we'll collect some initial data, and we build a predictive model, in this case called fit surrogate model, to understand the relationship between the input and output. And then we develop a rule using the information from the previous experiment to guide what we should do in the next experiment. So we do that using acquisition functions to guide us. And then we conduct the next round of experiment. And of course, often here, with the new round of data, we can update our surrogate model to make it more accurately being able to describe the relation between the input and output. And we can continue this process until we meet our stopping criteria. And at that point, we say we have completed a Bayesian optimization process, allowing us to optimize our process. So here's you may be thinking, why Bayesian optimization is called Bayesian optimization? It's because fundamentally, we're using Bayes' theorem to update our prior belief. In this case, it's the surrogate model being updated in light of new evidence, which is the new round of experiment we conducted and collect data. So in this lecture, we're not going to go through the mathematics formulation of the Bayes' theorem, but I really recommend the video shown on the slide, which is from my colleague, Professor Steve Brownton, which gives a detailed explanation of the conditional probability as well as the Bayes' theorem for those who are interested. So our goal of building a Bayesian optimization framework is often to achieve a cost and data-efficient way to optimize our process through iterative learning. Fundamentally, this is the concept of design an experiment based on ideas of whether we want to pre-plan everything or we want to update our experimental plan as we collect more data. Often, when we are using Bayesian optimization, we want to benchmark our framework with the traditional design experiment. For example, we can benchmark our Bayesian optimization against the full factorial. So this is an example of the traditional design of experiment. And say if we are in a process, again, to make our thin film semiconductors, we are interested in what's the temperature we need to use, and also we are interested in, let's say, the time of the annealing process. It's a short time, so it's in seconds. So maybe we want to study between 100 Celsius degree, so this is 200, 300, 400, degrees Celsius, and also say between 10 seconds, 20 seconds, and 30 seconds. So we want to study like what is the maximum like property of the interest, in this case the quality of our thin films, and what is the best condition to achieve that. So what we can do is we can build a grid. So in this case, we will sample at these specific conditions of interest. So in this case, what we are doing is that we are collecting 12 experiments, and that leads to 12 observables. And we learn from these 12 observables, and that gives us the expected and then later on predicted landscape, showing how our property of interest changes as a function of temperature and time. With BO, so it's a kind of data-driven DOE. Let's say an example of data-driven design of experiment. We still have our grid. So temperature, time, say this is 30, 20, 10, and we have 100, 200, 300, and 400. And we have our grid. So the difference is that in this case, instead of taking 12 observables, we first, let's say, conduct 3 experiments. And we learn from these 3 observables. And based on that, we say, hey, these will be the next set we should collect. So there'll be another 3. And we go from there. And another 3. At this point, maybe from these 9 observables, we already have a good understanding of where the maximum and minimum points are within this parameter space, and we can stop there. Or if not, we'll continue, and then we collect the rest of the points. So in this case, what it is doing is that instead of one-time learning, we are having iterative learning. As we plan the experiment, we collect more data, and then we plan the next set of experiment in an iterative fashion. That is how we can conduct our iterative learning by sequentially design our experiment. So now taking one step back and considering the broader context of using data-driven optimization techniques such as Bayesian optimization, is that we often Bayesian optimization is very powerful in optimizing a costly black box function. And in this case, often in real-world engineering challenges, we have some input. As the input parameters we're interested in tuning, and we have our output, and it may be noisy, and maybe we don't have many observables because it's expensive to run a lot of experiments. And in this case, trying to use a Bayesian optimization to find out what is this black box function linking our input and output is a very powerful way for us to save experimental budget and still effectively navigating large parameter space to achieve the optimization goals. With that, thank you very much for listening, and see you next time.